For this terminal velocity example, we're going to use our mass m is 4 kilograms, our drag coefficient gamma is 0.5 kilograms per second, and then the gravitational pull of the Earth is 9.8 meters per second squared. Right, we also have that the drag is proportional to the velocity. So then we have the differential equation for that. It's mv prime is equal to negative mg minus gamma v. Right, so let's go ahead and plug in our values. So we have m is 4, so we have 4 v prime is going to equal negative 4 times 9.8 for gravity of the Earth. Then we have minus gamma, so 0.5 times v. Right now, the goal here is to draw a direction field, and then we're also going to be asked to look for the terminal velocity. So let's go ahead and do that. So the terminal velocity is when v prime is equal to 0. Right? If you're at terminal velocity, you're not falling faster, you're not slowing down, so you're staying exactly at the same velocity. Right, and so we're going to go ahead and solve for that. It's also going to help us draw the direction field. So we have 4v prime, so it's really 4 times 0 equals, we still have negative 4 times 9.8. And we have minus 0.5 times v. Right, so here, right, it's this the left-hand side here is just 0. So I'm going to move the 4 times 9.8 over to the left. So we get negative 4, sorry, positive 4 since I moved it over, added it to both sides. So 4 times 9.8 is equal to negative 0.5 v. Then if I want to solve for v, I can multiply both sides by negative 2, right? That's negative 1/2. Multiply by both sides by negative 2, we get negative 2 times 4 times 9.8 equals v. And then if you actually compute that out, it's negative 78.4 equals v. And right, this does make sense. The terminal velocity is negative because we have positive velocity going upward. And right, so it's going to reach terminal velocity when the object is falling. So terminal velocity does make sense to be negative here. All right, so let's just go ahead and draw a direction field, and it's going to be a fairly quick one. So we're not going to care too much about the magnitude of the slope lines. We're just going to care if the magnitude is positive, so upward slope, negative, so downward slope, or 0, so just flat horizontal line slope. All right, so let's go ahead and draw in here the terminal velocity. So that was negative 78.4. And then just so we have a little bit of reference, let's say this is negative 88.4. And then up here we'll have negative 68.4. And all right, I'll leave those in, but I really wish I had done flat lines. So right in here, we've got the terminal velocity. So v prime is 0 at negative 78.4. So this one is a bunch of horizontal lines. Right? And now we're going to ask, okay, well, if we're at a number that's less negative, is that going to be negative slope, positive slope, or 0 slope? Probably not 0. Intuitively, they should be going down because the terminal velocity is going to be attracting, right? No matter how fast you throw the ball, and no matter how fast you throw it down or up, it's going to approach terminal velocity over time. If you do put in negative 68.4 into this equation, you do end up with v prime is 0. V prime is negative. So up here, we're just going to have downward facing lines. Right? You put in negative 88.4 into here, you're going to end up with a positive v prime. So that's going to be when the negative 0.5 times negative 88.4 is going to overcome the negative 9.4 times 9.8. These are going to be upward lines. And then they will get a little bit shallower as you get closer. I think I did that okay. And they'll end up getting, pretty almost flat, but still approaching as you get closer. So let me just draw those in here. All right, that would be the direction field. One more thing is, it's a little annoying to, compute these numbers all the time. We could have solved for the terminal velocity just with m and g and gamma. If we had done that, so we have m times v prime is equal to negative mg minus gamma v. So terminal velocity, we have v prime equals 0. Well, then we end up with 0 equals negative mg minus gamma v. And if you solve for that, you'll end up with mg gets moved to the left, and then we can multiply by negative gamma, so negative 1 over gamma. So the terminal velocity v is equal to negative mg over gamma. So you can also use that in the future, but keep in mind this only works when the velocity is proportional. When the drag is proportional to the velocity.